All right, so let's move to a slightly different topic for which we will use paths and so on eventually. It's the question of connectivity. So let's forget a bit about paths and walks for now and ask ourselves the following question. How well connected is a connected graph? So what do I mean by this? Look at the following two graphs. Both are connected, but G2 is somehow better than G1. You have to agree, it's more connected. So if you build a city where you put the roads as in G1, then if you have a big stone falling on any road, there is no way around it. Traffic will stop. You will isolate half the city or part of the city. In G2, you have alternative routes. So the graph G2 is a bit more robust. You need to take away more edges to get it to be disconnected. So this is the notion that we will now make precise. So let's look at a connected graph. A disconnecting set is a set of edges so that when you remove them, you get a disconnected graph. So if you go back here, let's say call this edge A, this edge B, this edge E, F, these are G, H, I. So if I remove the two edges E and F, I will get a disconnected graph because this vertex will be by itself. Same if I remove all three vertices G, H, I. Or if I remove all of these five vertices, I will still get an even more disconnected graph. In this graph, if I remove either of A or B or both, I will get a disconnected graph. So, for example, in G1, you had the set of A is a disconnecting set, the set of B is a disconnecting set, the set of both A, B is a disconnecting set, and so on. And in G2, say you had the set S equals EF, or you can take S equal G, H, I, and so on. And a disconnecting set that is minimal, meaning it doesn't contain a subset, a proper subset that is also a disconnecting set, is called a cut set. So if you again look at these examples, then this set is a cut set consisting of two vertices. This set is a cut set. In this graph, for example, taking just A or just B, this is a cut set. Why is this a cut set? Because if I remove only, say, G and H and not I, this graph will remain connected. And same if I only remove G and I or H and I. So a cut set is sort of the smallest, a minimal set that you can remove to make the graph disconnected. And a cut set that only has one edge is called a bridge. This is, the idea is that if you have some sort of graph here and then you have a river and then you have, river is not a precise term, then this is a bridge because if I remove just this one edge, the graph will become disconnected. So if you have a cut set, then the removal of that cut set will make the graph disconnected, yes, but the new graph will have exactly two connected components. Why two? Think about it for a moment. I'll give you the answer shortly. So if by removing S you get three components or four components, then you have removed too many edges. Then you could have already disconnected the graph by removing fewer edges than you did. So your cut set wasn't a cut set because you could do with a subset of it and still disconnect the graph. So for example, going back to this case, if I both remove A and B, I will get three components. This component, and this component. But I shouldn't remove both A and B. I could have removed a subset, for example, just A. Then I would have ended up with two components, and so on. So these notions are most useful when you talk about connected graphs, but they can also be useful when you talk about disconnected graphs. So basically, a disconnecting set is a set that if you remove those edges, you'll get a graph with more connected components than you started with. And a minimal disconnecting set is called a cut set. So you can define these for disconnected graphs, but most of the time when we will deal with these terms, we will be talking about graphs that were connected from the start, and by removing these edges, they become disconnected. So now we come to our stated aim of doing all this, namely we want to define a measure of how robust or well-connected a graph is. So we define the edge connectivity of a connected graph to be the number of edges in the smallest cut set possible. In other words, this is the smallest number of edges you will have to remove to destroy the connectedness of the graph and make it disconnected. Let's look at our previous example. So G1, remember, was such that it was enough to remove really one edge and any one edge so that the graph becomes disconnected. So since it's enough to remove one edge, then the minimal number to remove is 1, since the graph is connected to start with, so the edge connectivity is 1. What about G2? Think for a moment what lambda of G2 is. So what cut sets do we have? We had one example of a cut set, this GHI, that's one cut set. It has 3, so I know that it's enough to remove 3 vertices. It's 3 edges to make the graph disconnected. So the edge connectivity is at most 3, but maybe we can do better. And indeed we can. So we have this cut set consisting of E and F. That's already 2 vertices. So indeed, I can improve this to 2. Now, is there any single edge that I can remove to make the graph disconnected? No, you can double check. So in fact, lambda of G2 is equal to 2. Now you might find it confusing that we defined cut sets to be minimal, and now I'm telling you that some cut sets are bigger than others. What does minimal mean? Minimal doesn't mean that it has the least possible number of edges. It means that it doesn't have a subset of its own. So it means that if I'm only choosing edges between GH and I cannot satisfy myself with 2 edges or just 1 edge. I have to take all 3. But maybe somewhere else in the graph there's a cut set of 2 edges, and indeed there was in the case. And to define edge connectivity, you're looking for the smallest cut set. So this is the edge connectivity. And you call a graph K edge connected if the edge connectivity is at least K. So G1 is 1 edge connected. I'm abbreviating this EC. This is G1. G2 is also 1 edge connected because its edge connectivity was 2. It's also 2 edge connected, but it's not 3 edge connected. So that's just the terminology for how robust the graph is. Now we can characterize what it means to be 2 edge connected. So this business of cut sets seemed to be a bit weird and non-intuitive. Here's a theorem that tells you that a graph is 2 edge connected if and only if any 2 distinct vertices can be joined by 2 different paths. 2 paths with no edges in common. So the picture is this. So if you have X and Y, what you want is something like this, maybe. And this is this idea that we had in the beginning, that if you have a city, if you have 2 different roads that don't use the same chunks of road between 2 places, then you're good. If a tree blows down on one road, you can always take the other. So your graph is two-edge connected. The proof of this I leave as an exercise, if you want to look at it. It's a special case of a much more difficult proof, theorem by Menga from 1927 that generalizes this to any k. So a graph is k-edge connected, where k is 2, 3, 4, or whatever, if and only if any two distinct vertices can be joined by k paths such that no two paths have an edge in common. So this proof, if we get time, we will deal with this when we talk about matching problems at the very end of the course. By the way, what does it mean to be one-edge connected? Well, according to Menger's theorem, one-edge connected means that any two distinct vertices are joined by one path. Then the rest is a void condition. So then this just means connected, because we defined, or we looked at the characterization of connectedness as being the existence of a path between any two vertices. So far, we've talked about removing edges and testing how robust a graph is by removing edges. Instead, you can look at it the other way around and ask about removing vertices. So if you have a connected graph, then a separating set is somehow the vertex analog of a disconnecting set. A separating set is a set of vertices so that when you remove it, you end up with a disconnected graph. So let's look at this graph, for example. Let's call the vertices x, y, z, and w. So what is G if we remove the vertex x? Well, this is the graph that just has y, z, and w, because remember, the difference between removing vertices and edges is when you remove a vertex, you have to remove all the edges incident to it. So this is connected. So this is not a separating set. But if you look at G minus y, well, if I remove y and all the edges that are incident to it, I just get this. And this is indeed disconnected, so this is separating. And in the same way that we defined edge connectivity, we can define vertex connectivity. And that is the size of the smallest separating set in G, if such a set exists. So why may such a set not exist? Pause and think about this. Okay, so here's an example for you. Let's look at this example, the three cycle, also known as the three complete graph. Whichever vertex I remove, I will end up with a path with two vertices. If I remove this vertex, what is left are these two vertices. And if I also remove this vertex, what I'm left with is this vertex. But the point is, whatever I remove, I am getting a connected graph left. So there is no vertices that I can remove to make the graph disconnected. While for edges, I could always remove edges to make the graph disconnected. But for vertices, it's different. And in fact, you can prove, and this is a fun exercise that I want you to think about why this is the case, prove that if you have a simple connected graph, then the graph has a separating set if and only if it isn't a complete graph. So complete graphs are somehow the only ones that do not have separating sets. They are so well connected that you cannot remove any vertices or sets of vertices to make them disconnected. Also, you can think about what if you don't require the graph to be simple, then what can you say? When does the graph has a separating set? But if we look at graphs that do have separating sets, then the vertex connectivity is, in a sense, the smallest number of vertices that you can remove to make the remaining graph disconnected. Not just in a sense, this is actually what it is. So in the same way that we defined what it meant for a graph to be k-edge connected, we can define what it means to be k-vertex connected. So remember, go back to the definition of k-edge connected. K-edge connected meant that the edge connectivity of the graph is greater than or equal to k. So if you remove any less than k edges, the graph will still be connected. We want to define a similar thing for vertices. We have to be a bit roundabout, so the definition of k-vertex connected, well, you want the graph to have more than k vertices, and it stays connected whenever you remove a set with less than k vertices. If you're not dealing with a complete graph, this actually means that the vertex connectivity is at least k. So this is the analogous concept for vertices. It's slightly less useful than edge connectivity. So if you're comfortable with edge connectivity and this looks weird, wait a moment and go back to it later. Menger, who was apparently very fond of these things, also formulated a similar theorem for vertex connectivity. So a graph is k-vertex connected if any two distinct vertices can be joined by k paths that have no vertices in common between any two of them, except the start and end vertices, of course. So remember, k-edge connected was equivalent to the existence of k paths that were edge disjoint, and now we want our k paths to be vertex disjoint. So there is a subtle point. K-vertex connected is a word that's often abbreviated to k-connected. When you see k-connected, most often it means k-vertex connected, but sometimes, and actually in our book, it means k-edge connected. So be careful. I will always be clear with what I mean, so I will always say k-vertex connected and k-edge connected. And for us, the most useful concept is that of k-edge connected. But in short, what we have done with defining k-vertex connectivity and k-edge connectivity and all that is that we have notions to talk about how robust a graph is, how much you have to take away from the graph to make it disconnected. And thanks to Menger's theorems, we can formulate this as the existence of paths. So this is how paths are useful to make an abstract notion a bit more concrete.